Hi there, this is the video lecture for Chapter 4, Section 2. Some of what we cover today is going to feel familiar because we'll be doing some of the same types of formulas we've done before with other types of distributions. Just make sure you're keeping your notation straight and marking what each formula is for. Don't worry, you'll get it. I want to warn you ahead of time that this video moves kind of quickly. Take advantage of the fact that you have control over the video. Pause and rewind when you need to catch up or take notes. I'm not expecting you to memorize this stuff. Okay, let's get to it. Welcome to the video for Chapter 4, Section 2. Today we're going to be talking about a specific type of discrete probability called a binomial distribution. Here's what we're going to learn today. How to determine whether a probability experiment is a binomial experiment. How to find binomial probabilities using the binomial probability formula. We're going to talk about some shortcuts with technology and the formulas and the different tables that you can use to help solve these types of problems. We're going to talk about the graphs of these distributions, and we're going to find the mean, variance, and standard deviation of a binomial probability distribution. So some probability experiments only have exactly two outcomes per trial, a success or a failure. So for example, when a basketball player makes a free throw, either they make the basket or they don't. There's no in between. So these success-failure probability experiments are called binomial experiments. The prefix, of course, meaning two for exactly two outcomes. So binomial experiments satisfy four very specific conditions. The first is that a binomial experiment has a fixed number of trials. So we'll be dealing with the value of n being the sample size, or the number of trials in the experiment. And what's important about them is that they are independent of each other. A person tossing a head when they toss a coin does not affect whether the next time they toss a coin they will get a heads or a tails. Each of these tosses are independent of each other. We also have a fixed probability of success, so the notation we use is P of S, or lowercase p, to talk about the probability of successful trials, and we use P of F, or lowercase q, for a failure. Again, these are fixed for each of the trials. Also, the sum of the probability of success and the probability of failure equals 1. So if you know the probability of success, you can subtract it from 1 and you have the probability of failure, and vice versa. The fourth condition is that the random variable x is supposed to count the number of successful trials, and because a binomial experiment is a discrete probability experiment, the value of x is going to be a non-negative integer value, 0, 1, 2, 3, and so on. It's counting up the number of successful trials out of n trials. Okay, let's do a quick example to give us some context. From a standard deck of cards, you randomly pick one card. You note whether the card is a heart, and then replace it. You do this 4 times. How is this a binomial experiment? Well, we need to go through the 4 conditions. First of all, the number of trials is 4, so we can name the fixed number of trials, and we can say that they are independent because the card is replaced each time, so none of the trials are dependent on anything that happened in a previous trial. We can also see that there are only 2 choices. Either a card is a heart or it isn't. Our probability for success and failure is fixed for each of the independent trials. So we say this lowercase p is the probability of drawing a heart card. So that means p is equal to 1/4. There are 4 suits in the deck, so drawing a heart would be the probability of 1/4, 1 out of 4 possible suits. And since the only other outcome is a failure, not a heart, then we know the probability of failure is going to be 3/4, which is all of the other cards, or 1 minus 1/4. Lastly, our condition for making this binomial is how the value of x is being recorded. Well, again, this is a discrete random variable x, and it's supposed to be counting the number of times that we're successful out of our total number of trials. So x could really be anything in this case from 0 to 4 out of 4 tries. Maybe none of them are hearts, or exactly one of them is, or 2, etc. So the value of x is anything from 0 to 4. These are very specific conditions to check for, but they're pretty easy to pick out. Let's try a few more practice problems. Decide whether each experiment is a binomial experiment. If it is, specify the values of n, p, and q, and list the possible values of the random variable x. Number 1. A certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. Okay, so first, do we have a set number of trials? Yes, we have 8 trials because the doctor has performed 8 surgeries. And the trials are independent because one surgery doesn't depend on the outcome of another. Okay, what about the next condition? Do we have just 2 possible outcomes, success or failure? Yes, they told us that they have an 85% chance of success. That actually tells us it's a binomial probability and also gives us the value for p, or 0.85. And since this is a fixed probability, we can subtract that from 1 to find the third condition, our probability of failure, which would be 0.15. What about the random variable x? Can we determine a set that would include successful outcomes? Yes, any number from 0 to 8 could be successful. So yes, it meets the conditions for a binomial experiment. All right, let's do another. Number 2. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Well, the first condition is the number of trials and whether or not they are independent from each other. We can say that there are 3 trials because that's how many marbles are taken from the jar, but we don't have independent trials here. Our key phrase here is without replacement. When the marbles are not replaced, it changes the number of total marbles to choose from. There are 20 to start with, but when you take one out and you don't replace it, the second trial only has 19 to choose from. You're also possibly affecting the number of red marbles to choose from, too, if you chose a red marble the first time and don't replace it, because there are 5 red marbles to start with, and if you pick one the first time and don't replace it, there are now only 4. Conclusion is that this is definitely not independent, so this would not be a binomial experiment. Now, once we have determined whether an experiment is a binomial experiment, we then need to know how to solve this type of probability problem, one that has exactly X successes and N trials. To do this, we use this binomial probability formula. Now, I know this looks kind of like a bear of a problem, but I promise it's not that bad. Once you've used it a few times, you'll realize it's just a few pieces put together. Okay, let's talk about those pieces. The way you read this formula is it's really 3 parts. Here is a combination of successes, X successes if I have N trials, and then X successes, and N minus X, or the remainder, failures, and all of that is multiplied together. So we have the formula for the combination. Remember, it sort of factors out the leftovers on the bottom with a subtraction and the need for them to be in any specific order with the x factorial. Now, why are we using combination and not permutation, you might ask? Because the order doesn't matter. In a combination, we're concerned with how many successes we have, not with whether the first and third trials were successful. So we definitely want to use combination here. Then we have the successes, p to the x, and the failures, q to the n minus x. If you think about it, this looks very similar to something we've worked with before, the multiplication rule. Remember the probability of a and b equals probability of a times probability of b? When a and b are independent events, we saw that before. Well, we know that these are independent events because that's one of the conditions of it being a binomial experiment. So we apply that here to get p of x times q of n minus x. We're doing the same thing. And here are what all the letters in the formula stand for. Okay, think you're up for plugging some examples into this? Sure you are. Let's try it. Okay, rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Okay, first of all, we need to make sure this is a binomial experiment. Do we have a fixed number of trials? Yes, there were 3 patients or 3 trials. Are there definitely 2 outcomes, success and failure? Yes, and they gave us success is 90% or p equals 0.90, which would mean that q equals 0.10. We found that by subtracting 1 minus 0.90. Can we figure out the value of x by random variable counts of the number of successful surgeries? Yes, there would be anywhere from 0 to 3 successful surgeries or trials. So it clears all the conditions and it is a binomial experiment. Now we just need to plug everything in. We have our values for n, p, q, and x. N, or 3, goes in the numerator and denominator. X, or 2, goes in the denominator in both places. and in the exponent of p, or 9/10. P, or 9/10, with x, or 2, as the exponent. Then q, or 1/10, with the difference of n minus x, which is 1, as the exponent. If we do this by hand, we can do the subtraction in the denominator of the fraction, which just gives us 3 factorial over 2 factorial times 1 factorial, which is 1. If we multiply out 3 times 2 factorial, we can factor the 2 factorial out of both the numerator and the denominator, and just have the 3 remaining from the fraction. Then we take the 9/10 to the second power to get 81/100. 1/10 remains the same as it is raised to the first power. Multiply that by 3 and we get 0.243. Now, how could we do this with the calculator? Well, one way would be to do the following. Start with the combination part of the formula by typing in the number for n, in this case 3. Then press the math key. Arrow over to the probability menu, then arrow down to or press the number 3 option. Then type the number for x, in this case 2. Arrow over to get out of the sub-index area. For p, type open parentheses, then the numerator, in this case 9, then the division symbol key, then the denominator, in this case 10, then close parentheses, then the caret or exponent symbol, and the number for x, in this case 2. Okay, then for q, type open parentheses, then just the numerator, in this case 1, then the division symbol key, then the denominator, in this case 10, then close parentheses, then the caret or exponent symbol, and the number for n minus x, in this case 1, or you could skip this step in this case since it doesn't change the value. Then press enter, then press enter again to calculate. That should give you the same answer that we got before. If it didn't, make sure you're putting parentheses in the right place. Okay, I'm going to give you just a second to get some of these notes down. Pause the video if you need to. Alright, let's do another example. In a survey, U.S. adults were asked how often they go online. The results are shown in the figure. 6 adults who participated in the survey are randomly selected and asked whether they go online several times a day. That's one of the choices you can see in the figure. Construct a binomial probability distribution for the number who respond that they go online several times a day. Okay, so what we're wanting you to do is create a table similar to the frequency table that we created several sections ago. It will have the values of x, which are our possible number of successes, and our probabilities, using the different values of x. So we would do the formula for each value of x to create the table. So let's look at what they've given us. Our value of n is 6. Our values for p and q for the question they've asked us are 0.48 for p and 0.52 for q, because they specifically asked about the several times a day category, and the percentage for that category is 48%. And our values of x can be anywhere from 0 to 6 because our sample space is 6 adults. So we plug these into our calculator. That should give you this first value here. Okay, try the next one on your own. That would be with the x value of 1, but all the other values stay the same. Okay, I'm going to be nice and give you the rest of these. Did you get the second one right? You should have gotten 0.109. If not, make sure you're raising the right parts to the right powers. They can get a little tricky in there. Parentheses are necessary to keep the combinations separate from the p and q values. Alright, so these values are our probabilities that each number of successes for that category of several times a day would occur. And this is what the binomial distribution would look like. Very similar to other distributions we've done. This has the x value, which, if you remember, is the number of successes, and the probability of each of those numbers of successes occurring. So when you're told to construct a binomial distribution, this is what you're doing. Okay, so here's all the work we would have done to create this table. What if I told you there was a simpler way to do all of this? Of course you'd be thrilled, right? I certainly would. From here on out, we're going to use what's called the binomial probability density function on your calculator, or binom PDF. The values that it needs are the value of n, p, and the various values of x. Okay, let's look closer at how to do this. To use the binomial probability density function, you first have to get to it. So, press the second key, then the vars or variable key to pick the dist or distribution option above it. Arrow up to near the bottom of the list and find and select the option that says A Binomial PDF. Make sure you get the right one, not CDF. It needs to say PDF at the end. Then press Enter to select it. Depending on your calculator, there will be different ways for you to select your variables. You may need to press Enter between them or type them in and put commas between them and close your parentheses. But regardless of how you enter them, you need to put in the variables in order. The number of trials, or your N value, then your P value in decimal form, and the X value you're working with. Press Enter, then Enter again to calculate. How much simpler was that? Okay, so to enter a previous example, press Second, then Vars, then arrow up and select Binomial PDF, then Enter, then type in your variables for N, 6, P, 0.48, and X, let's do 1, and then Enter and Enter. You should get 0.109 like you did previously. Now here's a very handy thing to know. You can find the other values of X without having to enter even that small amount again too. When you're on the main screen and you've just finished one calculation for X with the Binomial PDF formula, simply press Second Enter to bring the formula back. Then use your left arrow a few times to get to the X value, the last number, and type over it with the new X value. Then press Enter again. Nice, huh? Take a few minutes to make sure you have these notes and are comfortable finding these on your calculator. Alright, let's take that formula for a spin with an example. A survey found that 75% of U.S. adults are experiencing digital device fatigue. This is the state of mental exhaustion caused by concurrent and excessive use of digital devices such as smartphones and tablet computers. You randomly select 100 adults. What is the probability that exactly 66 are experiencing digital device fatigue? Use technology to find the probability. Okay, so first we need to verify that this is a binomial experiment. What do we look at first? Well, is there a fixed number of trials? Yes. There were 100 adults that were selected, so N equals 100. This amount is fixed. Are the trials independent? Well, whether or not I have digital device fatigue doesn't affect whether you're experiencing it or not. So yes, they are independent. Is there a clear success or failure outcome? Yes, either someone is experiencing it or they are not. And they have given us a percentage of 0.75. So that would mean that the failure rate is Q equals 0.25, because that is 1 minus 0.75. Is the random value discrete? Can I list the number of successes? Yes, it can be anywhere from 0 to 100. All right, so this is a binomial experiment. So the question is asking, what is the probability that exactly 66 are experiencing digital device fatigue? So that is my X, 66. So I plug this into my calculator with the values shown. N equals 100, P equals 75, and X equals 66. Do that calculation now. It's possible to find binomial probabilities on other technologies too, as you can imagine, but let's see if you were able to get the same result on the TI-84 as they did here. You should have gotten 0.011167 or something close to that. How'd you do? Alright, let's expand this a little bit into the world of probabilities, because we're not likely to be asked just one part of a question like that. We're going to be asked multiple parts. Let's look at another example to see what I mean. A survey found that 22% of U.S. adults say that the economy, unemployment, and jobs are the most important problems facing the U.S. today. You randomly select 4 adults and ask them whether the economy, unemployment, and jobs are the most important problems facing the U.S. today. Find the probability that 1, exactly 2 of them respond yes, 2, at least 2 of them respond yes, and 3, fewer than 2 of them respond yes. If you read that quickly, you may have thought they were all the same question, but I bet your math eye has gotten better and you're recognizing now that these are going to require some different calculations. So let's dive in. first one asked about exactly 2 adults responding yes. So using n equals 4, p equals 0.22, because they gave us that percentage, and x equals 2, what do we get? Well, here's what you get when you plug it in the previous way that we showed, but you should get the same using the binomial PDF formula. The probability that exactly 2 adults will respond yes is 0.177, or very close to that. Okay, let's do the next one. This one asks to find the probability that at least 2 adults will respond yes. To do this one, we're going to need to find all the values of the probabilities of x values from 2 to 4, since n equals 4. So we need to find the probability for x equals 2, 3, and 4. Plug this into the formula for those values. Here's what the process looks like. So we have the formula, and we have our values. We're going to use the same values of n, p, and q, but we're going to use different x values for each time we plug in the formula. Remember the shortcut I told you about how to change the x after you've plugged in everything and done the function once? If you don't remember, that was second enter, and it will bring back the formula for you, and you use your arrow key to go back to the last number, and then just type over that last number with the new x value. Okay, this is a process, and in order to get your final answer, you have to add these together. So probability of 2, probability of 3, and probability of 4. So when you add those together, you get about 0.212 chance that at least 2 people will respond yes. Okay, last one. To find the probability that fewer than 2 adults will respond yes, we need to find the values where x equals 0 and 1. Here's what that process looks like. And notice that we are using 2 different values for x again. So you have to go through that process once for 0 and once for 1. The probability that fewer than 2 adults would respond yes is 0.788. Okay, nice work. Okay, let's look at another way we can solve these problems. Your e-text actually has a binomial probabilities table in the appendix that you can use. We'll use it for this example so you can see how it works. About 5% of workers aged 16 years and older in the United States commute to their jobs by using public transportation, excluding taxis. You randomly select 8 workers. What is the probability that exactly 3 use public transportation to get to work? Use a table to find the probability. Well, we can quickly evaluate this to be a binomial experiment because it has a fixed number of trials, so n equals 8 workers. Either a worker commutes via public transportation or they don't, so there's a clear success or failure, success being that they do, so p equals 0.05, and they are asking what the probability that exactly 3 of them out of the 8 do use public transportation, so our x 3. So if we look at the table in the back of the book, it looks like this. We use the value at the top first. That is our p value. And we find the correct volume for our p value. If you remember, ours was 0.05. So we found that value, and this is the column that we use to narrow down our search. That's our probability of success. So we're looking at 0.05. Then we look for the appropriate n, or sample size. So see that outer number? That's our n value. Then we look inside at the other column of numbers for our x, in this case 3, and we follow that row across until it meets the column of the p value. That's where we find our probability at the intersection of those, 0.005. Okay, so according to the table, the probability is 0.005. Okay, now we're going to switch gears to some familiar terms. Mean, variance, and standard deviation. Except this time we're going to find them for a binomial distribution. The thing is, the formulas for a binomial distribution are super easy. The formulas that we learned in 4.1 will work for a binomial distribution, but because of the particular properties of a binomial distribution, they simplify beautifully into what you see here. The mean is just n times p, the variance is n times p times q, and the standard deviation is the square root of n times p times q. Okay, take a minute to write these wherever you're writing notation and formulas. All right, let's try an example, shall we? In Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Interpret the results and determine any unusual values. Okay, so as before, we need to establish that it's a binomial experiment. In this particular case, days are either cloudy or they're not. I know weather can be less direct than that, but for this example, we're saying cloudy or not. There are a fixed number of trials. The month of June has 30 days, so we're saying n equals 30. Did they give us a success probability? Yes, they said 56%, which is 0.56, so that is our p-value. And we have only to subtract that from 1 to get our q value, which would be 0.44. And those are the only numbers we need. So now let's find our formulas. First, the mean. Mu equals n times p. Our n value is 30 and p equals 0.56, so 30 times 0.56 equals 16.8. So we found our mean. That was simple, right? Next is variance. Sigma squared equals n times p times q. So we already have n times p, which is 16.8, so we take that times 0.44 and we get about 7.4. So that is our variance. Now if we take the square root of that result, we get our standard deviation, which is about 2.7. Very good. So how do we interpret this? Well, first off, we have our values. Mean is 16.8, variance is about 7.4, and standard deviation is 2.7. What does this mean? Well, on average, there are 16.8 cloudy days during the month of June. The standard deviation is about 2.7 days. Values that are more than 2 standard deviations from the mean are considered unusual. That's how we tell when something is unusual. So, if we figure that out for lower than the mean, that would be this first formula, 16.8 minus 2 times 2.7, because that was our standard deviation, equals 11.4, which means a June with 11 cloudy days or less would be unusual. Then we can do the same for the higher number. 16.8 plus 2 times 2.7 equals 22.2, which means a June with 23 cloudy days or more would be unusual. Okay, nicely done. That does it for this section. I will see you in the next video.